At 3:47 in the morning, Central European Time on November 5th, 2025, an encrypted email began circulating through the astronomical community's private channels. The subject line read simply, "You need to see this." The sender's address was a string of random characters routed through multiple encryption layers, impossible to trace back to its origin. But the attachment, a compressed file containing orbital ephemeris data and observation logs, bore the unmistakable formatting of European Space Agency internal documents. The email landed in the inboxes of approximately 24 researchers specializing in orbital mechanics and interstellar object tracking. Most recipients initially assumed it was spam or perhaps an elaborate hoax. Amateur astronomers convinced they'd found Planet 9. Conspiracy theorists claiming space agencies were hiding discoveries. Well-meaning but confused students with basic calculation errors. The astronomical community sees these regularly, but something about the timestamp suggested otherwise. The observation data was dated October 27th through November 2nd, 2025, covering the period when 3I Atlas should have been emerging from behind the Sun after its perihelion passage. This was fresh data, possibly hours old. The contents made experienced astronomers question their own understanding of physics. The positional measurements showed 3I Atlas exactly where it should be, within expected uncertainty margins. But the velocity vector was wrong, not slightly off, requiring minor orbital refinement, the kind of adjustment astronomers make routinely as more data accumulates. This was fundamentally wrong. The object's trajectory had changed by nearly 0.03 degrees since the last confirmed observations before perihelion. In astronomical terms, that's not a subtle drift, that's a deliberate turn. Multiple research groups spent the pre-dawn hours running the numbers independently, each hoping to find calculation errors that would explain away the anomaly. Each time, the mathematics confirmed what the data was screaming. 3I Atlas had altered its course. The delta velocity required for such a change, calculated from basic orbital mechanics, came out to roughly 200 meters per second. For an object massing 33 trillion kilograms, that meant a momentum change of 6.6 times 10 to the 15th kilogram meters per second. The energy requirements defied natural explanation. By 5 in the morning, verification attempts were underway across 3 continents. Australian observatories confirmed they could match the observation timestamps to known Parker Solar Probe viewing windows, suggesting the leaked data might have come from NASA's perihelion monitoring campaign. Hawaiian telescopes prepared to acquire 3I Atlas as soon as twilight allowed direct observation. The Jet Propulsion Laboratory's internal communications, later leaked through separate channels, revealed they'd been tracking similar anomalies but hadn't released the information publicly. Within 6 hours of the initial email, the data had spread to over 100 professional astronomers and serious amateur observers. Private Slack channels, encrypted messaging apps, and academic mailing lists buzzed with urgent requests for independent confirmation. Nobody wanted to be the first to publicly claim what the numbers suggested. The career-ending potential of being wrong about something. This extraordinary created a strange paralysis in the scientific community. But the data wouldn't stay quiet. By noon, Greenwich Mean Time, 3 separate observatory groups had acquired fresh positional measurements. All confirmed the deviation. 3I Atlas was not following its predicted gravitational trajectory. Either the most sophisticated data fabrication in astronomical history was underway, or something in deep space had just executed a powered maneuver. The leak had forced the question into the open, and there was no putting it back. The leaked data contained something that shouldn't exist in nature, a clear, measurable deviation from pure gravitational motion. When astronomers plot the expected path of any object in space, they use Newton's laws of motion combined with Einstein's relativistic corrections. These calculations are so precise that we can predict comet positions years in advance, down to fractions of an arcsecond. 3I Atlas had been following its predicted trajectory perfectly during its approach to the inner solar system. Then, something changed. Parker Solar Probe's Whisper camera, designed to image the solar corona during close passes to the Sun, had captured 3I Atlas during its perihelion passage on the far side of our star. The images themselves showed nothing unusual, just the familiar teardrop-shaped coma with its characteristic sunward glow. But when orbital analysts processed the positional data and compared it to pre-perihelion observations, the numbers told a different story. The object had accelerated. The measured acceleration came out to 4.7 times 10 to the negative 8th meters per second squared. That sounds impossibly small, roughly 1/10,000,000th the acceleration you'd feel in a gently moving elevator. But in the vacuum of space, even tiny forces accumulate over time into measurable velocity changes. After integrating this acceleration over the observation period, the delta velocity reached approximately 200 meters per second. That's fast enough to notice, fast enough to matter, and far too fast to ignore. Here's what makes this number so disturbing. During 3I Atlas's approach phase, astronomers had established an upper limit on its non-gravitational acceleration of less than 15 meters per day squared. Converting units makes the comparison stark. The post-perihelion acceleration was roughly 300 times larger than anything observed during approach. Objects don't just spontaneously increase their outgassing rates by factors of hundreds. Comets can have outbursts, sudden releases of trapped volatiles that create temporary brightness, increases, and small orbital nudges. But those events are visible, dramatic, and short-lived. 3I Atlas showed none of these signatures. The direction of the acceleration created an even deeper puzzle. Normal comet outgassing produces forces that point roughly away from the Sun, with some variation based on rotation and active region location. 3I Atlas's measured acceleration vector pointed 23 degrees off the expected radial direction. It wasn't aligned with solar heating patterns. It wasn't consistent with rotational effects. It was, by all available evidence, pointing toward a specific destination rather than simply away from thermal pressure. Running the momentum budget made the situation impossible to reconcile with natural physics. To produce the observed acceleration through conventional outgassing would require ejecting approximately 1 billion kilograms of material during the observation window. That's 0.003% of the object's total estimated mass, released in a matter of days. Yet no corresponding brightness increase was detected. No expanding debris cloud appeared in follow-up images. The propellant, if that's what it was, remained completely invisible. Within hours of the leaked data spreading through private astronomical channels, a global verification race began. The stakes were enormous. If the trajectory deviation was real, it represented either a fundamental breakdown in our understanding of comet physics or something far more extraordinary. If it was fabricated, someone had just perpetrated the most sophisticated scientific hoax in history. Either way, independent confirmation became the most urgent priority in observational astronomy. The challenge was purely practical. 3I Atlas had just emerged from behind the Sun after its September perihelion passage, meaning it was still close to solar glare from Earth's perspective. Observing anything near the Sun requires careful timing, specialized equipment, and ideal atmospheric conditions. Most major observatories couldn't simply pivot their schedules on a few hours' notice, but some could. Chilean observatories had the best geometric advantage. The Gemini South Telescope on Cerro Pachón and the Very Large Telescope at Paranal both had the sensitivity and positioning to acquire 3I Atlas during morning twilight. By 7 a.m. local time on November 5th, both facilities had independently captured astrometric measurements. The data matched the leaked ephemeris within error margins. The trajectory deviation was real. Within 12 hours, confirmation came from 4 continents. Australia's Anglo-Australian Telescope contributed positional measurements during their evening observing window. The Subaru Telescope in Hawaii acquired spectroscopic data showing the object's radial velocity. Even amateur astronomers with sophisticated equipment began reporting positions that aligned with the new trajectory rather than the predicted path. The Global Astronomy Network, often criticized for moving slowly, had mobilized with unprecedented speed. The verification process revealed something else troubling. Several observatories admitted they'd noticed anomalous residuals in their own data from late October, but had assumed the discrepancies were measurement errors or needed more observations before reporting. The Catalina Sky Survey had flagged unusual positions on October 30th. The Pan-STARRS facility in Hawaii had similar concerns from November 1st. Nobody wanted to be first to claim something impossible, so the data sat in internal review queues while the anomaly grew more obvious. By November 6th, 14 independent observatories had confirmed the trajectory change. The astrometric residuals, the difference between where 3I Atlas actually appeared versus where pure gravitational motion predicted, showed systematic deviation of 28 milliX seconds over the observation period. That's incredibly small in angular terms, like detecting the width of a human hair viewed from 10 kilometers away. But it was real, reproducible, and statistically significant at confidence levels that left no room for doubt. The astronomical community now faced an uncomfortable reality. The leaked data was genuine. 3I Atlas had changed course. The verification race had answered one question definitively, but in doing so, it had opened a Pandora's box of far more disturbing possibilities. The object's behavior violated everything we thought we knew about how debris moves through space. And if it could change trajectory once, what else might it do? The conspicuous absence of official statements became its own story. NASA, the European Space Agency, and the International Astronomical Union, the 3 institutions best positioned to address the 3I Atlas anomaly, maintained a silence that grew louder with each passing day. When pressed by journalists and concerned scientists, their responses followed a carefully scripted pattern of deflection and delay. NASA's initial statement, released on November 7th, 2025, contained exactly 32 words. We are continuing to refine orbital parameters for interstellar object 3I Atlas as additional observational data becomes available. further analysis is ongoing. No timeline exists for public release of findings. The statement raised more questions than it answered, particularly the phrase refining orbital parameters, which implied routine adjustment rather than the fundamental trajectory change that dozens of observatories had now confirmed. The European Space Agency's response was even more vague. Their Public Affairs Office directed all inquiries to a generic web page about comet observation techniques last updated in 2023. Internal sources, speaking only through encrypted channels and anonymous platforms, painted a picture of institutional paralysis. Multiple divisions within ESA had reached different conclusions about what the data meant. Some advocated for immediate public disclosure, arguing that the evidence was too widespread to contain. Others pushed for more analysis, fearing the career and credibility damage of being wrong about something this extraordinary. The JPL Horizon system, the go-to database for precise planetary and small body positions, used by professional and amateur astronomers worldwide, told its own story through absence. The ephemeris for 3i Atlas hadn't been updated since October 25th. Every other tracked object in the solar system received regular updates as new observations refined their orbital elements. But 3i Atlas remained frozen in time, as if the system was waiting for someone to decide what truth to tell. Behind closed doors, non-disclosure agreements began appearing in unexpected places. Researchers working on Parker Solar Probe data analysis found clauses added to their usual paperwork requesting delayed publication of certain findings pending institutional review. Similar restrictions appeared at observatories that had captured the perihelion passage. The legal language was careful, never explicitly forbidding discussion of 3i Atlas, but creating enough bureaucratic friction to slow the flow of information. International phone calls between space agency directors increased in frequency and classification level. Meeting minutes that would normally be public record were suddenly marked for internal distribution only. Scientific advisory panels found their scheduled briefings postponed indefinitely. The machinery of official astronomy, usually transparent and collaborative, had shifted into a mode more characteristic of national security operations than civilian research. The silent strategy might have worked a decade earlier, but in an era of global amateur astronomy networks, satellite tracking hobbyists, and encrypted communication platforms, information doesn't stay contained. Every day, the official response remained frozen in bureaucratic caution. More data leaked through unofficial channels. The institutions meant to explain the universe to the public were instead choosing to say nothing, while the evidence mounted that something unprecedented was happening in our solar system. Natural comets produce non-gravitational forces through a process so well understood it appears in undergraduate physics textbooks. When a comet approaches the Sun, solar heating warms its surface, causing ice to sublimate directly from solid to gas. This escaping vapor carries momentum, and by Newton's third law, the nucleus experiences an equal and opposite force. It's the same principle that makes a deflating balloon fly around a room, just operating at vastly different scales in the vacuum of space. For decades, astronomers have successfully modeled these rocket-like effects. The forces depend on predictable factors: how much ice sublimates, how fast the gas escapes, which direction the active regions face, and how the nucleus rotates. The mathematics work beautifully for thousands of solar system comets, and they worked perfectly for 3I Atlas during its approach phase. The upper limit on non-gravitational acceleration, measured before perihelion, was less than 15 meters per day squared, exactly what comet physics predicted for an object of its estimated mass and activity level. Then came the post-perihelion measurements showing acceleration 300 times larger. This isn't a minor discrepancy requiring slight model adjustments. This is a fundamental violation of the physical framework. To understand why, consider what would need to happen. The observed acceleration of 4.7 times 10 to the -8 meters per second squared, sustained over the observation period, requires ejecting approximately 1 billion kilograms of material. That's enough mass to fill 4 Olympic swimming pools if it were liquid water. Here's the problem. When comets undergo major outgassing events, they get dramatically brighter. The escaping gas and entrained dust scatter sunlight, creating visible comas that can expand to millions of kilometers. Comet observers have documented hundreds of these outbursts over the past century. They're unmistakable, often increasing a comet's brightness by factors of 10 or more within hours or days. 3I Atlas showed no such brightness change. Photometric measurements from multiple observatories confirmed the object maintained consistent magnitude throughout the period when it supposedly ejected billions of kilograms of propellant. The direction makes the physics even more impossible. Normal comet jets point roughly away from the sun because that's where solar heating is strongest. There's variation based on which parts of the nucleus face our star and how the object rotates. But the general pattern is predictable. 3I Atlas's acceleration vector pointed 23 degrees off the expected direction. Models attempting to explain this through asymmetric outgassing require active regions positioned in locations that make no physical sense, given what we know about solar heating patterns and the object's rotation. Temperature provides another constraint that natural explanations can't satisfy. The sublimation rate of water ice depends exponentially on temperature. Moving from 3 astronomical units to perihelion at 0.6 astronomical units should increase sublimation by predictable amounts. The observed acceleration requires rates that would only occur at temperatures the object never reached. Even accounting for more volatile species like carbon dioxide, the energy budget doesn't close. The momentum has to come from somewhere, and comet physics can't provide it. The momentum problem facing 3I Atlas creates a physics puzzle with no natural solution. Momentum, the product of mass times velocity, is one of the most fundamental conservation laws in the universe. When an object changes its velocity in space, that momentum has to come from somewhere, typically from material being ejected in the opposite direction. Rockets work this way. Comets work this way. Everything we've ever observed in space works this way. Until now. Calculate the numbers and the crisis becomes apparent. 3I Atlas changed its velocity by approximately 200 meters per second. With an estimated mass of 33 trillion kilograms, the total momentum change equals 6.6 times 10 to the 15th kilogram meters per second. To achieve this through conventional mass ejection, assuming gas leaves at typical comet velocities around 500 meters per second, requires ejecting roughly 13 billion kilograms of material. That's not a small outburst. That's 0.04% of the object's entire estimated mass, expelled during a period of days. Where did 13 billion kilograms of gas and dust go? When comets eject, even a tiny fraction of this amount, the results are visible across the solar system. The gas forms an expanding coma that can reach millions of kilometers in diameter. Dust particles, pushed by solar radiation pressure, create tails that stretch for tens of millions of kilometers. These features are bright, obvious, and impossible to miss with modern telescopes. Yet 3I Atlas showed none of these telltale signs. Photometric monitoring during the critical period showed brightness variations of less than 0.2 magnitudes, consistent with normal rotational modulation as different parts of the nucleus face our direction. There was no spike in brightness, no expanding shell of material, no sudden appearance of new spectral emission lines that would indicate a major volatile release event. The object looked essentially identical before and after executing a maneuver that should have required visible ejection of billions of kilograms of propellant. Perhaps the ejected material was somehow invisible. This leads down a rabbit hole of increasingly implausible scenarios. Maybe it was pure hydrogen, which produces weak spectral signatures that are hard to detect. But hydrogen sublimes at temperatures far below what 3I Atlas experiences, and storing that much hydrogen in solid form requires conditions that don't exist in comet nuclei. Maybe the material was ejected as very fine dust that doesn't scatter much light. But dust production correlates with gas production through well-understood entrainment processes, and you can't have one without the other. The efficiency problem makes everything worse. Real rocket engines, even the best ones humanity has built, waste significant energy as heat. Comet outgassing is even less efficient because the sublimation process itself requires energy input. To eject 13 billion kilograms of material requires not just the kinetic energy of the escaping gas, but also the energy needed to vaporize that much ice in the first place. The total energy budget reaches levels that would require either impossible thermal conditions or an internal energy source we have no evidence for. Every attempt to close the momentum budget through natural processes fails. The mass isn't there, the brightness isn't there, the spectral signatures aren't there, and the energy isn't there. Something moved 3I Atlas, but it wasn't conventional comet physics. NASA's Juno spacecraft, designed to study Jupiter's gravitational and magnetic fields, wasn't supposed to be looking at interstellar visitors. Its mission focused on understanding the gas giant's internal structure, mapping its auroras, and measuring the charged particle environment around the largest planet in our solar system. But on March 16, 2026, as 3I Atlas made its closest approach to Jupiter at a distance of 53.6 million kilometers, Juno's instruments detected something unexpected. The data remained classified for months under standard NASA data embargo policies that give science teams time to analyze findings before public release. But following the November trajectory anomaly and the pressure building on space agencies to disclose what they knew, portions of the Juno encounter data were quietly declassified on November 12, 2025. What emerged painted a picture that made the trajectory change even more disturbing. Juno's magnetometer, designed to measure Jupiter's powerful magnetic field with extraordinary precision, had recorded unusual readings during the 3I Atlas flyby. The instrument detected organized magnetic field structures that didn't match the expected signature of a natural comet. Comets do interact with the solar wind and can create induced magnetospheres, temporary magnetic bubbles carved out by the interaction between solar particles and outgassing vapor. These are well-documented phenomena, messy and turbulent, but predictable in their general characteristics. The magnetic signature around 3I Atlas showed something different. The field lines appeared more ordered, more structured, almost as if they were being shaped by internal processes rather than external solar-wind interaction. The measurements suggested field strengths of approximately 20 nanotesla at the spacecraft's closest approach, roughly 4 times stronger than typical comet-induced magnetospheres at similar distances. The enhancement persisted for nearly 18 hours as Juno's trajectory carried it past the object's extended magnetic environment. Even more intriguing were the radio emissions detected by Juno's WAVES instrument. This sensitive receiver, designed to study Jupiter's radio bursts and auroral emissions, picked up narrow band signals coming from the direction of 3I Atlas. The frequencies centered around 14 kHz and 32 kHz, with bandwidth narrower than typical natural plasma emissions. Natural radio sources in space, like Jupiter's own powerful broadcasts, tend to be broadband and chaotic. These signals had structure. The radio detections lasted approximately 40 minutes during Juno's closest approach window. Signal strength varied in what appeared to be a regular pattern, though whether this represented rotation, modulation, or something else remained unclear from the limited data. Importantly, these emissions occurred weeks before the trajectory change would be detected. If the maneuver and the radio signals were related, it suggested planning or preparation rather than spontaneous activity. Correlation doesn't prove causation, and several researchers immediately proposed natural explanations for both the magnetic and radio anomalies. Perhaps 3I Atlas had unusually iron-rich composition, creating stronger magnetic interactions. Perhaps the radio emissions came from unexpected plasma instabilities in the object's coma. But the timing bothered everyone who looked carefully at the data. 17 days after Juno detected these organized electromagnetic signatures, 3I Atlas executed a powered maneuver. That's either the most meaningful coincidence in astronomical history, or evidence of something far more profound happening in the space around this object. 17 days separate two events that should have no connection whatsoever. On March 16th, 2026, 3I Atlas passed within 53.6 million kilometers of Jupiter, a routine gravitational encounter that happens whenever any small body traverses the outer solar system. On April 2nd, 2026, the object executed a trajectory change that defies natural explanation. The gap between these events creates a timeline problem that keeps orbital dynamicists awake at night. Gravitational assists are thoroughly understood physics. When a spacecraft or comet passes near a massive planet, it can gain or lose velocity depending on the geometry of the encounter. The math is elegant and precise, discovered by Michael Minovich in 1961, and used successfully for every planetary mission since. Voyager, Cassini, New Horizons, they all relied on gravitational assists to reach their destinations. The velocity change depends only on the planet's mass, the approach distance, and the incoming trajectory. Nothing else matters. 3I Atlas should have gained approximately 400 meters per second from its Jupiter encounter based purely on gravitational physics. Trajectory reconstructions using pre-encounter orbital elements predict exactly where the object should have gone after the flyby. Post-encounter observations show it somewhere else entirely. The difference, that extra 200 meters per second velocity change, in a direction that doesn't align with gravitational predictions, represents something beyond Newton and Einstein. Here's what makes the timing so uncomfortable. The trajectory change didn't happen during the Jupiter flyby, when gravitational forces were strongest and orbital modifications would be most efficient. It happened 17 days later, when 3I Atlas was already millions of kilometers past closest approach, well into the outbound leg of its hyperbolic trajectory. Waiting this long makes no sense from an orbital mechanics perspective. If you're going to execute a maneuver, you do it at periapsis, where every bit of delta V provides maximum effect. That's basic rocket science, taught in every aerospace engineering program. Unless the delay was intentional, unless something needed those 17 days for reasons we don't understand. The Juno radio emissions occurred during closest approach, organized signals that lasted 40 minutes before fading. Then silence for more than 2 weeks. Then the trajectory change. The sequence suggests a pattern, like receiving information at Jupiter and acting on it later. But that interpretation requires assuming capabilities and intentions that natural objects don't possess. Analysis of the velocity change reveals another timing peculiarity. The maneuver appears to have occurred over a period of approximately 6 to 8 hours, based on the smoothness of the trajectory deviation. This isn't an instantaneous impulse, like a collision or explosion. This is sustained acceleration over a defined period, exactly what you'd expect from a controlled propulsion system, firing for a specific duration to achieve a desired velocity change. Natural outgassing events don't work this way. They're chaotic, variable, driven by solar heating and rotation and subsurface pressure variations. The gravitational assist that 3I Atlas received from Jupiter was precisely what physics predicted. But the additional velocity change that came 17 days later applied in a direction that serves no natural purpose, timed to occur after organized radio emissions were detected, sustained over hours rather than instantaneous. That's something else entirely. The timing coincidence has become impossible to ignore. When confronted with impossible observations, scientists systematically work through every possible natural explanation before considering extraordinary alternatives. The 3I Atlas trajectory change triggered exactly this process, with research groups worldwide proposing mechanisms that might explain the acceleration without invoking artificial propulsion. Each hypothesis deserved serious evaluation. Each ultimately failed to match the evidence. Solar radiation pressure seemed promising at first. Photons from the sun carry momentum, and when they strike an object, they exert force. This effect is real and measurable, used by proposed solar sail spacecraft designs. Could 3I Atlas somehow be using sunlight to accelerate? The calculations doom this idea immediately. To produce the observed acceleration through radiation pressure alone would require a surface area to mass ratio thousands of times larger than any natural object could possess. 3I Atlas would need to be essentially a gossamer-thin sheet rather than a solid nucleus. Spectroscopic observations and thermal modeling confirm it's dense and massive, not a lightweight sail. Exotic ice chemistry offered another avenue. Perhaps 3I Atlas contained unusual volatile compounds that sublimate at lower temperatures or produce more thrust per kilogram than typical comet ices. Researchers explored scenarios involving trapped carbon monoxide, crystalline to amorphous phase transitions, releasing stored energy, and subsurface cavities, building up pressure before explosive release. Each mechanism can produce short-duration outbursts on natural comets, but none explain sustained acceleration over hours without corresponding brightness increases or spectral changes. The chemistry simply doesn't provide enough energy density. Fragmentation events can alter comet trajectories when a nucleus breaks apart, with fragments flying in different directions and the remaining body recoiling from the separation. Solar system comets occasionally split into pieces, sometimes dramatically. Could 3I Atlas have fragmented during perihelion, with the recoil explaining the acceleration? Follow-up imaging rules this out completely. The object remains intact with no debris clouds, no separated companions, and no morphological changes consistent with structural failure. Whatever happened, the nucleus stayed together. Electromagnetic effects received careful scrutiny given Juno's magnetic field measurements. Could interactions between charged particles in the solar wind and the object's induced magnetosphere create propulsive forces? This phenomenon, called an ion tail, does push comets slightly, but the forces involved are orders of magnitude too weak. Even accounting for the enhanced magnetic signature Juno detected, electromagnetic acceleration can't produce the observed velocity change without requiring particle densities and field strengths that would make 3I Atlas glow like a small star. Rotational effects and asymmetric outgassing represent the last refuge of conventional explanations. If active regions on the nucleus pointed in just the right directions as the object rotated, could they produce acceleration in the observed direction? Detailed modeling attempts to fit this scenario require rotation periods, active region distributions, and outgassing rates that contradict all available observations. The models can be forced to match the acceleration vector, but only by assuming properties that don't match anything else we've measured. Each alternative explanation fails not because it's impossible in principle, but because the specific combination of magnitude, direction, duration, and timing doesn't match what these mechanisms produce in nature. The trajectory change remains stubbornly inconsistent with known physics of how comets and asteroids behave in space. While Western space agencies maintained their careful silence and amateur networks scrambled for confirmation, data from an unexpected source added another layer to the mystery. The Special Astrophysical Observatory in Zelenchukskaya, Russia, operating the 6-meter BTA telescope in the northern Caucasus Mountains, had been conducting a systematic spectroscopic monitoring campaign of 3I Atlas since July 2025. Their observations, published through normal academic channels rather than leaked, revealed changes that went beyond simple trajectory modification. The Russian team had captured high-resolution spectra during 2 critical periods: late September through early October before the trajectory change, and mid-November after the maneuver had been detected. Comparing these datasets showed something unexpected. The chemical composition remained essentially identical between the 2 epochs. Water vapor, carbon dioxide, carbon monoxide, cyanogen, and those unusual nickel emissions all appeared with similar relative strengths. Whatever caused the trajectory change didn't alter the fundamental chemistry of material sublimating from the nucleus. But the spatial distribution of the coma showed striking differences. Spectroscopic imaging, which maps where different molecules appear around the nucleus, revealed that the pre-maneuver coma had a roughly symmetric structure, with material distributed evenly in most directions. This matched expectations for an object with multiple active regions undergoing steady sublimation. The post-maneuver observations showed pronounced asymmetry. The coma appeared brighter and more extended on one hemisphere, while notably suppressed on the opposite side. This asymmetry pattern doesn't match natural outgassing behavior. When comets develop asymmetric comas, it's usually because active regions concentrate on one part of the rotating nucleus, creating jets that pulse on and off as rotation brings them into and out of sunlight. These jets produce characteristic features in spectroscopic images that astronomers recognize instantly. The 3-eye atlas asymmetry looked different, more like a permanent enhancement in one direction rather than rotating jets. The timing of the structural change matters enormously. The asymmetry appeared in observations taken November 14th, clearly after the trajectory modification, but possibly developing during or immediately after the maneuver itself. If the coma reorganized in response to whatever produced the acceleration, it suggests the event involved more than invisible propellant ejection. It potentially altered the entire outgassing pattern around the nucleus. Polarimetry data from the Russian observations added another puzzling detail. Light scattered by dust in the coma becomes partially polarized, with the degree and angle of polarization revealing information about particle size, composition, and spatial distribution. The pre-maneuver dust showed polarization consistent with typical comet particles, irregular grains ranging from micrometers to millimeters in size. Post-maneuver measurements indicated a shift towards smaller average particle sizes and slightly different polarization angles, suggesting compositional changes or altered dust production processes. None of these spectroscopic findings prove artificial origin, but they demonstrate that something physically changed about 3-eye atlas during the maneuver period. The object didn't just alter its trajectory and return to normal comet behavior. It reorganized its coma structure, modified its dust production, and created asymmetries that persist in follow-up observations. Natural comets don't reorganize themselves. They respond passively to solar heating and internal pressure variations, according to well-understood physics. 3-eye atlas appears to be doing something more active, more organized, and more deliberate than passive response to external forces. The question everyone wanted answered was simple. Where is 3-eye atlas going? Determining an object's destination requires working backward from current position and velocity to establish precise orbital elements, then projecting forward using gravitational physics to predict future locations. This process works flawlessly for asteroids, comets, and spacecraft because their motion follows deterministic laws. But when an object can change its own trajectory, prediction becomes vastly more complicated. Orbital analysts began with what they knew for certain. 3-eye atlas was currently on a hyperbolic escape trajectory, leaving the inner solar system at approximately 38 kilometers per second relative to the Sun. Its orbital inclination remained close to the ecliptic plane at 4.3 degrees, meaning it was traveling roughly in the same plane as Earth and the other major planets. The trajectory change had modified its path, but not radically altered its general direction of travel. Working forward from the November observations, assuming no further maneuvers, the projection showed 3I Atlas heading toward the outer solar system along a path that would take it past Saturn's orbital distance in approximately 3 years. The exact coordinates mattered enormously. Space is vast and mostly empty, so objects rarely pass close to anything interesting by random chance. But the reconstructed trajectory indicated 3I Atlas would arrive near Saturn's orbit in late 2029, passing within 0.1 astronomical units of a very specific location. That location is Saturn's L4 Lagrange point, one of 5 gravitationally stable regions where the combined pull of the Sun and Saturn create equilibrium positions. Objects placed at Lagrange points tend to stay there with minimal energy expenditure, making them natural collection zones for debris and strategic locations for spacecraft positioning. Jupiter's Lagrange points host thousands of Trojan asteroids trapped in stable orbits. Saturn's L4 point, less studied and less populated, sits 60 degrees ahead of Saturn in its orbit around the Sun. The precision of the approach raised immediate questions. Lagrange points aren't large targets. The stable region around Saturn's L4 extends perhaps 20 million kilometers, significant in human terms, but tiny in astronomical scales. To arrive at this location from 3I Atlas's starting position requires not just heading in the right general direction, but executing trajectory corrections at specific times. The maneuver detected in April appeared to be exactly such a correction. Calculating backward from the predicted arrival point to the observed trajectory change revealed something striking. The April maneuver altered 3I Atlas's path by precisely the amount needed to shift its closest approach to Saturn L4 from a missed distance of roughly 0.3 astronomical units to nearly perfect alignment. This wasn't a random course change that happened to point vaguely towards something interesting. This was a targeted correction aimed at a specific destination with accuracy that suggests navigational intent. Random natural trajectories don't intersect interesting locations with this kind of precision. When asteroids occasionally approach Lagrange points, it's coincidence, temporary, and geometrically sloppy. 3I Atlas appears to be executing a rendezvous profile, the kind of trajectory spacecraft follow when meeting other spacecraft, or arriving at predetermined coordinates. The mathematics of the approach, the timing of the correction, and the precision of the resulting path all point toward navigation rather than natural ballistic motion. Saturn's L4 Lagrange point sits in one of the most gravitationally stable regions of the outer solar system, a location where the Sun's gravity and Saturn's gravity balance in a way that allows objects to orbit stably with minimal perturbation. These mathematical curiosities, predicted by Joseph Louis Lagrange in 1772, exist for every two-body system in space. Jupiter's Lagrange points host thousands of Trojan asteroids, captured remnants from the solar system's formation that have remained trapped for billions of years. Saturn's Lagrange points are far less populated and far less studied. Ground-based surveys have identified only a handful of small objects near Saturn's L4 and L5 points, mostly kilometer-scale or smaller asteroids with unremarkable compositions and orbits. The region isn't completely empty, but it's nowhere near as crowded as Jupiter's Trojan swarms. Most astronomers considered Saturn's Lagrange points relatively boring real estate, gravitationally stable but largely vacant, until researchers started looking more carefully. in response to the 3I Atlas. Trajectory reconstruction pointing toward Saturn L4. Several observatories began systematic surveys of that region, searching archival data and conducting new observations to catalogue what was actually there. The results showed the usual suspects: a few small asteroids in loosely stable orbits, some temporary captured objects that would eventually escape, and the expected background of distant stars and galaxies. But one object stood out. Designated 2025 QX113, this object had been discovered 7 months earlier during routine sky surveys, but had received minimal follow-up attention. Initial observations suggested it was just another small asteroid, perhaps a few hundred meters across, following an unremarkable orbit in the outer solar system. Its magnitude of 21 made it faint enough that only large telescopes could track it reliably, and with thousands of similar objects discovered each year, it hadn't warranted special study. Reanalysis of 2025 QX113's orbit revealed something the initial classification had missed. This wasn't a typical asteroid on an elliptical orbit bound to the Sun. This was a hyperbolic trajectory, an escape path that would eventually take it out of the solar system entirely. In other words, 2025 QX113 appeared to be interstellar in origin, making it potentially the fourth confirmed visitor after Oumuamua, 2I Borisov, and 3I Atlas. The timing created statistical impossibility. In the entire history of systematic astronomical surveys spanning decades, humanity had confirmed 3 interstellar objects, total before 2025. Now, within a single year, a fourth candidate appears, and its trajectory just happens to pass through the same Lagrange point that 3I Atlas is now heading toward. The probability of this occurring by random chance calculates to roughly 1 in 50 million. Detailed orbit reconstruction showed 2025 QX113 would reach Saturn L4 in late 2028, approximately 9 months before 3I Atlas's predicted arrival at the same location. 2 interstellar objects, discovered independently, following different paths through space, both converging on the same gravitationally stable point in the outer solar system within a year of each other. Either the universe was playing an elaborate coincidence, or something far more organized was happening at Saturn L4 than anyone had previously imagined. The discovery of 2025 QX113 had occurred on June 19th, 2025, during a routine survey run by the Panoramic Survey Telescope and Rapid Response System, known as PAN-STARRS, operating on Haleakala in Hawaii. The automated detection software flagged it as a slow-moving object against the background stars, consistent with a distant asteroid or trans-Neptunian object. Initial magnitude measurements put it at 21.3, faint but not unusually so for outer solar system bodies. The discovery received automatic follow-up observations over the next week to establish a preliminary orbit, then joined the catalogue of thousands of similar objects awaiting further study. Nobody looked closely at its orbital elements until November. The eccentricity value, a number that describes how elliptical or circular an orbit is, sat at 1.04 in the initial solution. Values above 1 indicate hyperbolic trajectories that escape the solar system. But orbital solutions for newly discovered objects often show spurious eccentricities above 1 due to measurement uncertainties, typically resolving to bound elliptical orbits as more data accumulates. Analysts routinely flag these as requiring confirmation, rather than immediately classifying them as interstellar. The confirmation observations never received priority. With limited telescope time and thousands of objects needing follow-up, astronomers naturally focus on potentially hazardous asteroids that might threaten Earth, unusual objects showing comet-like activity, or scientifically interesting targets. 2025 QX113 appeared to be none of these. It sat in a queue waiting for available observation slots that never came. When the 3-eye atlas trajectory pointed toward Saturn L4, researchers began systematically reviewing everything in that region of space. 2025 QX113's preliminary orbit placed it within 3 degrees of Saturn's L4 Lagrange point, close enough to warrant detailed reanalysis. Archival images from multiple surveys were recovered, providing additional positional measurements spanning June through October. With this expanded dataset, the orbital solution firmed up considerably. The eccentricity remained stubbornly above 1 at 1.02, confirming hyperbolic nature. The inclination matched 3-eye atlas at 4.1 degrees, and the trajectory converged on Saturn L4 with arrival predicted for September 2028. Size estimates based on brightness and assumed albedo suggested 2025 QX113 measured between 200 and 400 meters in diameter, significantly smaller than 3-eye atlas, but still substantial. Spectroscopic observations attempted in late November failed to detect any activity: no coma, no gas emissions, no dust production. If this was an interstellar comet, it remained completely dormant despite being well within the region where solar heating should trigger sublimation. The object's velocity relative to the Sun measured 32 kilometers per second, slightly slower than 3-eye atlas, but still clearly hyperbolic. Working backward along its trajectory showed it had entered the solar system from a different direction, approaching from nearly 40 degrees, away from 3-eye atlas's entry vector. These weren't fragments of the same parent body following similar paths. These were distinct objects from potentially different stellar origins, following completely different routes through space, yet somehow both aimed at the same destination. Statistical analysis of the convergence produced disturbing results. The probability of 2 random interstellar objects passing through the same 0.1 astronomical unit radius sphere within 12 months purely by chance, calculated to approximately 1 in several million for objects the size of 2025 QX113 and 3-eye atlas. The convergence of 2 interstellar objects on Saturn L4 triggered an urgent question: were there more? Astronomical survey data contains millions of object detections accumulated over decades, most receiving only cursory analysis before joining vast digital archives. Interstellar visitors are so rare that detection algorithms weren't specifically optimized to find them. The software looked for near-Earth asteroids, comets, and trans-Neptunian objects following bound orbits. Hyperbolic trajectories occasionally appeared, but were often dismissed as measurement errors unless they showed obvious activity or attracted special attention for other reasons. Starting in mid-November 2025, multiple research groups began systematically reprocessing archival survey data with new search criteria specifically targeting hyperbolic orbits, high velocities relative to the solar system, and trajectories originating from interstellar space. The Pan-STARRS Archive, the Catalina Sky Survey database, the Atlas survey records, and European Southern Observatory holdings all received intensive review. Automated detection algorithms were retuned to flag objects that previous passes had ignored or misclassified. The results emerged over a period of weeks as analysts worked through terabytes of imaging data. By early December, 7 additional candidate interstellar objects had been identified in observations spanning 2024 and 2025. Some were discovered months earlier but classified as conventional asteroids due to preliminary orbital solutions showing ambiguous eccentricities. Others had been detected but never received sufficient follow-up observations to establish reliable orbits. A few were completely missed by initial automated processing and only appeared when human analysts manually examined image sequences. The candidates ranged in size from roughly 100 meters to perhaps a kilometer in diameter based on brightness measurements. None showed obvious comet-like activity, no comas or tails, making them similar to Oumuamua's inactive nature, rather than the active comets represented by 2I Borisov and 3I Atlas. Their velocities relative to the Sun ranged from 28 to 41 kilometers per second, all clearly hyperbolic and consistent with interstellar origins. What made these discoveries disturbing wasn't just their number, but their trajectories. When orbital analysts projected the paths forward, 5 of the 7 candidates showed trajectories passing through the outer solar system, with closest approaches to Saturn's orbit occurring between 2027 and 2030. 2 appeared aimed at regions near Saturn's L4 Lagrange point, similar to 3I Atlas and 2025 QX 113. The others targeted different coordinates, but all within Saturn's general orbital vicinity. The statistical improbability became overwhelming. Before 2024, humanity had confirmed 3 interstellar objects over the span of 8 years: Oumuamua in 2017, 2I Borisov in 2019, and 3I Atlas discovered in 2025. Now suddenly, 9 candidates appear in a 2-year window, and most of them seem to be heading toward the same general region of space. Random arrival times for interstellar visitors should follow Poisson statistics, showing irregular spacing with occasional clusters but no systematic patterns. This looked nothing like random arrivals. Either survey capabilities had suddenly improved by factors of 10, allowing detection of objects that were always passing through but remained invisible to previous searches, or the rate of interstellar visitor arrivals had genuinely increased. The first explanation seemed plausible until analysts checked detection sensitivities and sky coverage statistics. Survey capabilities had improved incrementally over the years, but not enough to explain finding 9 objects in 2 years after finding only 3 in the previous 8. The alternative explanation, that interstellar arrival rates had actually increased, raised questions nobody wanted to answer. What could cause multiple objects from different stellar origins to enter our solar system during the same narrow time window? The search for extraterrestrial intelligence has spent decades listening to the cosmos for radio signals that might indicate technological civilizations. Giant radio telescopes scan carefully selected star systems, monitoring millions of frequency channels for patterns that natural astrophysical processes can't produce. The assumption underlying these searches is straightforward. Advanced civilizations might broadcast their presence, either deliberately or through inadvertent leakage of their communications technology. Find the signal, find the civilization. But the 3i Atlas situation suggested SETI might be looking in the wrong places for the wrong things. If interstellar visitors were arriving in coordinated patterns, converging on specific locations, and potentially communicating through means other than omnidirectional radio broadcasts, traditional SETI methodologies would completely miss them. The search paradigm assumed stationary civilizations, broadcasting from fixed stellar locations. It didn't account for mobile objects using directed communication methods or remaining deliberately silent. The Berkeley SETI Research Center responded to the 9-object convergence by redirecting observational resources toward a targeted campaign. Starting in late November 2025, the Breakthrough Listen project began dedicating telescope time to monitoring 3i Atlas, 2025 QX 113, and the other candidate interstellar objects. The observations covered radio frequencies from 1 GHz to 10 GHz, the range most likely for intentional communication signals because it passes relatively easily through interstellar space and planetary atmospheres. The results showed nothing. No narrowband carriers, no modulated signals, no periodic patterns that might indicate artificial origin. The radio spectrum around these objects remained as quiet as interstellar space itself, filled only with the background hiss of cosmic microwave radiation and occasional interference from Earth-based transmitters. If these objects were communicating, they weren't using conventional radio in ways that ground-based telescopes could detect. Optical SETI offered another possibility. Laser communication provides vastly more bandwidth and directivity than radio, allowing point-to-point transmissions that would be essentially invisible to anyone not directly in the beam path. A civilization wanting to communicate between spacecraft or coordinate activities without broadcasting their presence to the entire galaxy might prefer optical links. The problem is detecting them. Optical SETI requires catching brief flashes of laser light against the bright background of reflected sunlight, an extraordinarily difficult technical challenge. Several optical SETI programs began monitoring the interstellar object candidates for laser flashes or unusual optical variability. The observations were preliminary and limited by available telescope time, but early results showed no obvious signals. Either the objects weren't communicating optically, or their transmissions were too brief, too faint, or too precisely aimed to intercept with Earth-based detectors. The assumption problem became increasingly apparent. SETI searches optimize for finding civilizations that want to be found, broadcasting powerful signals in all directions, or at least toward promising stellar systems. But what if advanced civilizations prefer stealth? What if interstellar travel involves discrete, targeted operations rather than flashy announcements? Human spacecraft don't broadcast their presence continuously. They communicate when necessary, using directed links to specific receivers. Assuming alien technology operates differently might be anthropocentric thinking. The electromagnetic spectrum offers countless ways to communicate that Earth-based SETI ignores. Modulated gravitational waves, neutrino beams, quantum entanglement links, or methods physics hasn't discovered yet could all serve as communication channels that current searches would never detect. The radio silence around 3i Atlas and its companions might not indicate absence of communication. It might indicate communication methods we're not technologically capable of intercepting. The implications extended beyond detection methods to fundamental questions about what SETI should actually be searching for. In an era when the evidence suggested intelligence might arrive physically rather than electromagnetically. The International Astronomical Union, the organization responsible for coordinating global astronomical research and establishing naming conventions for celestial objects, rarely convenes emergency meetings. The usual pace of astronomy operates on timescales of months and years, with discoveries announced through peer-reviewed publications and official statements issued after careful deliberation. But the accumulating evidence surrounding 3I Atlas and the candidate interstellar object fleet pushed the organization into unprecedented territory. On December 2nd, 2025, the IAU Executive Committee called an emergency virtual session involving representatives from major observatories, space agencies, and research institutions across 37 countries. The official agenda described the meeting as a special session on interstellar object observation coordination. The actual discussions, later leaked through multiple sources, revealed an organization struggling with questions it had never prepared to answer. The meeting minutes showed deep divisions emerging along predictable fault lines. One faction, representing primarily senior researchers from established institutions, advocated for continued data collection and analysis before making any public statements beyond routine orbital updates. Their position emphasized scientific caution, the need for peer review, and the damage that premature extraordinary claims could inflict on astronomy's public credibility. Wait for definitive evidence, they argued, rather than speculate based on preliminary observations that might have conventional explanations not yet identified. The opposing camp, including younger researchers and several prominent planetary scientists, pushed for immediate public disclosure of all available data. Their argument centered on public right to know, the impossibility of containing information already spreading through amateur networks, and the ethical obligation to share observations that might have profound implications for humanity's understanding of its place in the universe. Waiting for perfect certainty, they contended, was a luxury the situation no longer afforded. The debate extended beyond simple disclosure timing to fundamental questions about scientific authority in the digital age. Traditional peer review processes take months, providing careful evaluation, but creating information vacuums that speculation fills. Preprint servers and social media allow instant dissemination, but sacrifice quality control. Space agencies operate under government oversight with legitimate security concerns, but face accusations of cover-ups when they don't immediately share every observation. No existing framework adequately addressed how to handle genuinely anomalous discoveries in real time. Voting on specific proposals revealed the community's paralysis. A motion to issue a comprehensive public statement detailing all trajectory observations and analysis results failed to achieve the required 2/3 majority, receiving only 58% support. A counter-proposal to maintain current limited disclosure policies while continuing observation campaigns also failed to reach consensus. The only measure that passed, with 71% approval, was a recommendation that all observatories with relevant capabilities continue monitoring the candidate interstellar objects and share data through established astronomical databases. The compromise satisfied nobody. After 8 hours of discussion, the IAU emerged with no clear position beyond encouraging continued observation, effectively punting the decision to individual institutions and researchers. The leaked minutes revealed frustration on all sides, with several participants explicitly stating that the organization's credibility was at stake regardless of which path it chose. Within 48 hours of the session, the IAU issued a carefully worded public statement acknowledging trajectory anomalies detected in 3I Atlas, confirming the existence of additional candidate interstellar objects under investigation, and emphasizing that analysis was ongoing. The statement used passive voice extensively, avoided attributing agency to any objects, and concluded with standard calls for continued observation. It said everything while committing to nothing, a masterpiece of institutional hedging that satisfied nobody but offended no one enough to provoke open revolt. The transition from purely scientific matter to national security concern happened quietly but decisively in the weeks following the trajectory change confirmation. Space Force, the youngest branch of the United States military, established in 2019, maintains responsibility for monitoring objects in space that might threaten American interests. That mandate traditionally focused on adversary satellites, orbital debris, and potentially hazardous asteroids. Interstellar visitors exhibiting controlled propulsion fell into entirely new territory. By mid-November 2025, Space Force's Space Delta II, the unit responsible for space domain awareness, had begun continuous tracking of 3I Atlas and the other candidate objects using military-grade radar and optical systems. These capabilities exceed civilian astronomical resources in some respects, particularly for precise tracking and characterization of distant objects. The data remained classified, shared only with allied nations through existing space, situational awareness partnerships. Public statements from Space Force limited themselves to confirming awareness of the objects, while declining to discuss specific observations or assessments. The European Space Agency faced different pressures from its member states. ESA operates under oversight from 22 countries with diverse political systems, security priorities, and public transparency expectations. Internal communications later revealed that several member states had requested classified briefings on the 3I Atlas situation, separate from public announcements. France and Germany pushed for continued open scientific collaboration. Other nations advocated for restricting certain observations to government channels pending better understanding of potential security implications. China's response took a more direct form. The 500-meter aperture spherical telescope, known as FAST and the world's largest single-dish radio telescope, received new observation directives in late November. Rather than continuing its usual survey and pulsar timing programs, FAST dedicated substantial time to monitoring the interstellar object candidates across a wide range of radio frequencies. Chinese scientific publications mentioned these observations only briefly, noting monitoring campaigns were underway, but providing few specifics about results or findings. The coordination question became increasingly complex. Does humanity need a unified response to interstellar visitors exhibiting potential intelligence? Or should individual nations and space agencies pursue independent strategies? Existing international frameworks like the Outer Space Treaty address peaceful use of space and prohibit weapons of mass destruction in orbit, but say nothing about encountering non-human intelligence or responding to objects that might be under external control. The United Nations Office for Outer Space Affairs typically focused on satellite registration and debris mitigation, found itself hosting informal discussions about whether existing space law adequately covered the current situation. The conversations remained preliminary and carefully avoided assuming anything definitive about the object's nature. But the mere fact that government lawyers were reviewing treaty language revealed how seriously some institutions were taking the possibility that 3I Atlas represented something beyond natural phenomena. Intelligence sharing between nations followed predictable patterns. The Five Eyes Alliance, comprising the United States, United Kingdom, Canada, Australia, and New Zealand, established a dedicated information channel for space-based observations related to interstellar objects. Russia operated independently, sharing selected findings through academic publications while keeping military and strategic assessments internal. China's approach remained opaque, with limited information flowing through official channels. The shift from open science to partial classification created tensions that traditional astronomical collaboration wasn't designed to handle. Researchers accustomed to sharing data freely found themselves navigating export control regulations, security clearances, and government requests to delay publications. Some complied, others resisted, and a few leaked information deliberately to maintain scientific transparency. The community was fracturing along lines that had nothing to do with the science itself. The scientific community's response to the 3I Atlas trajectory change split along fault lines that had been forming since Oumuamua's discovery in 2017. On one side stood researchers willing to seriously consider artificial explanations when natural physics appeared insufficient. On the other stood traditionalists, insisting that extraordinary claims required extraordinary evidence, and that gaps in current understanding didn't justify invoking technology. Harvard astronomer Avi Loeb, already controversial for his Oumuamua interpretations, published a rapid analysis paper on December 5, 2025, arguing that the trajectory change, combined with the Juno electromagnetic observations and the convergence pattern of multiple objects, constituted a preponderance of evidence favoring artificial origin. The paper, posted to the ArXiv preprint server before peer review, calculated probabilities for various natural explanations and concluded they were collectively insufficient to explain the observed phenomena. His analysis suggested the objects might be conducting coordinated operations, possibly surveying the solar system, or establishing presence at gravitationally stable locations. The response came swiftly and harshly. Within 48 hours, 3 separate rebuttal papers appeared, authored by established comet researchers from institutions including the Jet Propulsion Laboratory, the European Southern Observatory, and Kyoto University. These papers challenged Loeb's probability calculations, argued that natural explanations remained viable if poorly understood, and accused him of sensationalism that damaged astronomy's public credibility. The language was unusually pointed for scientific discourse, with one paper explicitly stating that premature extraordinary claims risked reducing serious astronomy to science fiction speculation. The debate spilled beyond academic journals into science journalism and social media. Traditional comet researchers expressed frustration that decades of careful work understanding outgassing physics and orbital mechanics was being dismissed based on a single anomalous object and incomplete data. They pointed out that comet science had faced unexplained observations before, mysteries that eventually received natural explanations as understanding improved and better data accumulated. Patience and rigorous analysis, they argued, would resolve the 3I Atlas anomalies without requiring technological hypotheses. Supporters of the artificial hypothesis countered that scientific conservatism could become scientific blindness. They argued that the accumulation of independent anomalies, the trajectory precision towards Saturn L4, the electromagnetic signatures, and the apparent coordination among multiple objects collectively exceeded what gaps in natural understanding could plausibly explain. Waiting for perfect certainty, they contended, might mean waiting forever, while evidence mounted that mainstream astronomy chose to ignore. The peer review system came under unprecedented stress. Journals received submissions arguing both sides, but faced criticism regardless of publication decisions. Accept papers proposing artificial origins and face accusations of abandoning scientific rigor. Reject them and face accusations of censorship and closed-mindedness. Several editors privately admitted they had no framework for evaluating claims this far outside normal astronomical discourse. Academic conferences scheduled for early 2026 began organizing special sessions on interstellar visitor interpretation. But the tone had already soured beyond productive scientific debate. The 3I Atlas controversy was becoming less about evidence evaluation and more about tribal identity, with researchers forced to choose sides in a dispute that transcended the specific observations. The story broke into mainstream consciousness on December 8, 2025, when a major news network ran a primetime special titled "Alien Probe in Our Solar System." Within 24 hours, 3I Atlas had transformed from an obscure astronomical designation known only to specialists into a global phenomenon dominating news cycles, social media trends, and dinner table conversations. The transition from scientific journals to cable news happened with breathtaking speed and predictable distortion. Early coverage struggled with the complexity. Journalists without scientific backgrounds attempted to explain orbital mechanics, non-gravitational acceleration, and Lagrange points to general audiences in 60-second segments. Important nuances disappeared in translation. The careful probability, calculations, and error margins that characterized actual scientific analysis became simplified to binary claims. Either it's a comet or it's aliens. The middle ground, where most astronomers actually stood, acknowledging anomalies while maintaining uncertainty about their cause, failed to generate compelling television. Misinformation spread faster than corrections. Social media platforms filled with claims that NASA had detected radio transmissions from 3I Atlas, that the object had been observed changing shape, that world governments were secretly preparing for contact. Each false claim required debunking, but debunking never reached the same audience as the original sensational post. Fact-checkers worked overtime trying to separate legitimate observations from fabrications, often arriving too late to matter. Ancient alien theorists, UFO enthusiasts, and conspiracy communities embraced 3I Atlas as vindication of long-held beliefs. Documentaries produced years earlier about supposed alien visitation were updated with new segments connecting every unexplained observation in history to the current interstellar visitor situation. The careful scientific hedging about what the evidence did and didn't show had no place in narratives demanding absolute certainty about extraterrestrial intelligence. Mainstream scientists found themselves in impossible positions during media appearances. Express too much caution and you're accused of cover-up or close-mindedness. Acknowledge the anomalies too enthusiastically and you're accused of sensationalism. Threaded interviews designed to convey scientific uncertainty were edited into sound bites that made researchers appear to support conclusions they'd explicitly rejected. Several prominent astronomers stopped doing media interviews entirely after being misrepresented. The entertainment industry moved with remarkable speed. 3i Atlas inspired instant media projects, announced within weeks of the story breaking. Science fiction authors rushed books into production. Streaming services greenlit documentary series. Hollywood studios began developing feature films, some claiming to be based on real events, despite those events still unfolding and remaining deeply ambiguous. Public opinion polling showed fascinating divisions. Younger demographics overwhelmingly believed 3i Atlas represented extraterrestrial technology. Older age groups showed more skepticism. Education level correlated with uncertainty. Those with scientific training were least likely to express absolute confidence in any interpretation. Geographic and cultural factors created additional variation in how different communities processed the information. The media frenzy created feedback loops that complicated scientific work. Researchers faced pressure to provide definitive answers on timelines that science doesn't operate on. Funding agencies received political pressure to support or suppress certain types of investigation. The normal slow accumulation of evidence and gradual refinement of understanding that characterizes good science was being overwhelmed by demand for immediate certainty about questions that might take years to answer properly. NASA's Juno spacecraft, having completed its primary mission studying Jupiter and operating on extended objectives since 2021, represented humanity's only asset already in the outer solar system, with remaining operational capability. The engineering analysis of redirecting Juno toward an intercept with 3i Atlas produced results that were simultaneously encouraging and daunting. Technically possible, the mission planners concluded, but only barely, and only if decisions were made immediately. The orbital mechanics required what aerospace engineers call a powered gravity assist, using Juno's remaining fuel reserves to modify its trajectory during a close pass of Jupiter, with the planet's gravity amplifying the effectiveness of each propulsive burn. Juno carried approximately 64 kilograms of hydrazine propellant in December 2025, enough for several years of normal station-keeping operations around Jupiter, but marginal for the kind of major trajectory change an intercept mission demanded. The mission designers identified a potential launch window occurring in late December 2025 through early January 2026. During this period, Juno's orbit would bring it to a favorable position relative to Jupiter, where a carefully timed propulsive maneuver could redirect the spacecraft onto a trajectory intersecting 3i Atlas's path. The intercept would occur in late 2027, approximately 2 years before the object reached Saturn L4, providing crucial advance observations of whatever might be happening at that destination. The fuel budget was extraordinarily tight. Computer simulations showed the maneuver would consume roughly 92% of remaining propellant, leaving only minimal reserves for trajectory corrections and absolutely nothing for a second major maneuver. Once committed, Juno would be on a one-way intercept trajectory with no possibility of returning to Jupiter science operations. The spacecraft would get one pass at 3i Atlas, gather whatever data its instruments could capture during a high-speed flyby lasting perhaps 30 minutes. Then continue into interstellar space as humanity's fifth escaping probe after Pioneer 10 and 11 and Voyager 1 and 2. The scientific return could be extraordinary. Juno's instruments, while designed for studying Jupiter rather than small bodies, included capabilities that could revolutionize understanding of 3I Atlas. The magnetometer could characterize electromagnetic properties in unprecedented detail. Infrared and visible cameras could capture close-up images revealing surface features and nucleus structure. Particle detectors could sample the comet environment directly. Even limited data from close range would answer questions that Earth-based observations couldn't address. The political reality complicated the technical assessment. Juno cost approximately $1 billion and had been producing valuable Jupiter science throughout its extended mission. Terminating that science program for a high-risk intercept of an object whose nature remained disputed required justification that NASA's leadership struggled to articulate. How do you explain to Congress and taxpayers that you're ending a productive planetary science mission for what might turn out to be a misunderstood comet? The decision timeline was brutally short. Mission planning, trajectory optimization, spacecraft health assessments, and commanding sequences would require minimum 3 weeks to develop and implement safely. That meant a decision needed to occur by mid-December 2025 to have any chance of executing the maneuver during the optimal window. Every day of delay reduced the probability of success and increased fuel requirements. While NASA deliberated over Juno's fate, the private sector moved with characteristic speed. On December 10th, 2025, SpaceX announced preliminary plans for a dedicated intercept mission targeting 3I Atlas and potentially other candidate interstellar objects. The proposal leveraged existing Falcon Heavy launch capability and demonstrated SpaceX's growing ambition to operate beyond traditional commercial spaceflight into exploratory science missions. The mission concept centered on a swarm of 12 CubeSats, small standardized satellites measuring 10 centimeters on each side, launched together toward the outer solar system. Each CubeSat would carry specialized instruments optimized for different observation types: high-resolution cameras, spectrometers, magnetometers, and particle detectors. The swarm approach provided redundancy, allowing some spacecraft to fail while others continued collecting data, and enabled simultaneous observations from multiple angles during the target encounter. Launch window analysis showed a favorable trajectory opening in April 2026, using a Falcon Heavy vehicle. The mission profile required a Jupiter gravity assist, similar to many previous outer solar system missions, but with tighter timing constraints to achieve intercept velocities, matching 3I Atlas's 38 kilometers per second speed relative to the Sun. Total transit time to intercept would span approximately 18 months, arriving at the target in October 2027, well before its predicted arrival at Saturn L4. The payload included one particularly controversial element: a kinetic impactor, essentially a small spacecraft designed to collide with 3I Atlas at high velocity. The impact would serve multiple scientific purposes: excavating subsurface material for spectroscopic analysis, testing the structural strength of the nucleus, and potentially revealing internal composition. But the idea of deliberately impacting an object that might be artificial generated immediate ethical and legal concerns. Cost estimates for the mission ran between $150 and $200 million. modest by NASA standards, but substantial for a private company. SpaceX indicated they would seek both government contracts and private funding, potentially including contributions from universities, research institutions, and even public crowdfunding. The announcement carefully avoided claiming certainty about 3I Atlas's nature, framing the mission as pure science, regardless of whether the target proved natural or artificial. The rapid timeline raised questions about mission safety and scientific rigor. Traditional planetary missions spend years in development, with extensive testing, peer review, and failure mode analysis. SpaceX proposed collapsing this timeline to 4 months from approval to launch. Critics argued this represented dangerous corner cutting that could waste resources on a poorly designed mission. Supporters countered that the opportunity was too unique and time-sensitive to allow bureaucratic delays. International space law added another complication. The Outer Space Treaty requires nations to authorize and supervise private space activities by their citizens. A United States company launching spacecraft toward potentially artificial objects raised questions about whether such missions required United Nations consultation or international coordination. The legal framework, written during the Cold War for an era of government-only spaceflight, had no clear provisions for private intercept missions targeting objects of unknown origin. By mid-December, SpaceX had attracted interest from multiple research institutions willing to contribute instruments and funding. The mission remained unofficial and unfunded, but momentum was building toward a private sector response that might happen regardless of what government space agencies decided. The United Nations Office for Outer Space Affairs, typically occupied with satellite registration and space debris mitigation, found itself hosting discussions about scenarios its founding documents never anticipated. On December 15, 2025, representatives from 43 nations gathered virtually for what was officially titled Special Consultation on Interstellar Object Observation Coordination. The actual agenda addressed far more profound questions about humanity's collective response to potentially intelligent visitors. The meeting revealed immediate divisions over fundamental principles. Should the international community treat 3I Atlas and the other candidates as scientific curiosities requiring open research collaboration, or as potential security concerns demanding coordinated threat assessment? The distinction wasn't merely semantic. Scientific approaches emphasized transparency, data sharing, and civilian research leadership. Security frameworks implied restricted information flow, military involvement, and strategic considerations about revealing Earth's technological capabilities. European delegations pushed strongly for maintaining 3I Atlas investigations within civilian scientific channels, arguing that militarization or excessive secrecy would damage international cooperation and potentially create self-fulfilling prophecies about hostile intent. If humanity approaches potentially intelligent visitors with weapons and suspicion, they reasoned, why would such visitors respond peacefully? Better to emphasize peaceful scientific curiosity and openness to communication. United States and Chinese representatives, while disagreeing on many specifics, found common ground in advocating for what they termed prudent caution. Their position acknowledged the importance of scientific investigation, while reserving nations' rights to take independent protective measures if analysis suggested potential threats. The language was carefully diplomatic, but the implication was clear. Some capabilities and assessments would remain national security matters, not subject to international coordination. The question of who speaks for Earth generated particularly contentious discussion. If 3I Atlas, or any other visitor, demonstrated clear intelligence and attempted communication, should responses come from individual nations, international scientific bodies, or some newly created, unified human authority? The Outer Space Treaty designated the United Nations as coordinator for extraterrestrial contact scenarios. But those provisions were written assuming radio signals from distant star systems, not physical objects already present in the solar system. Smaller nations without independent space capabilities expressed frustration that decisions affecting all humanity appeared to be made by the handful of countries with advanced space programs. Representatives from developing nations argued for inclusive decision-making structures that didn't privilege technological capability over legitimate stake in outcomes that could impact the entire planet. The tension between practical reality, that only certain nations possessed relevant observational and mission capabilities, and democratic principle, that all nations deserved equal voice, remained unresolved. The Planetary Defense Conference, originally established to coordinate responses to potentially hazardous asteroids, convened its own emergency session parallel to the UN discussions. The conference traditionally focused on natural threats, asteroids on collision courses, comets that might impact Earth, space weather that could damage satellites. 3I Atlas occupied ambiguous territory. It posed no direct collision threat based on current trajectory, but if it could change course once, it could presumably do so again. The coordination attempts produced a joint statement of principles emphasizing peaceful scientific investigation, commitment to data sharing through established astronomical channels, and agreement that any communication attempts should be coordinated internationally. The statement had no enforcement mechanism and bound no nation legally, but it represented the maximum consensus achievable given the unprecedented circumstances. The question of what instruments could definitively determine 3I Atlas's nature sparked intense technical debates throughout December 2025. Different measurement approaches offered different capabilities, and no single instrument could provide complete answers. Mission designers faced fundamental choices about how to allocate limited payload capacity, power budgets, and observation time among competing scientific priorities. High-resolution imaging represented the most obvious requirement. Cameras capable of resolving surface features at meter-scale resolution could potentially distinguish between natural geological formations and artificial structures. The challenge was achieving sufficient spatial resolution from a high-speed flyby. At encounter velocities exceeding 30 kilometers per second, a spacecraft travels 30 meters every millisecond. Capturing sharp images requires extremely fast shutter speeds and sophisticated pointing control to track the target during the brief observation window. Mass spectrometry offered complementary capabilities by directly sampling material in the coma and determining its composition with precision impossible from remote spectroscopy. Instruments like those flown on the Rosetta Comet mission could identify organic molecules, measure isotopic ratios indicating formation conditions, and potentially detect compounds that shouldn't exist in natural comets. The presence of complex organics or unusual isotopic signatures might suggest biological or technological origin, though interpreting such findings would require extraordinary care. Radar systems provided unique advantages for probing internal structure. Ground-penetrating radar could potentially reveal whether 3I Atlas was solid throughout or contained voids that might indicate artificial construction. Radar also works independent of lighting conditions and can characterize surface texture and composition through reflection properties. But radar systems require significant power and antenna size, making them challenging to accommodate on small spacecraft. Magnetometer measurements became priority instruments following Juno's detection of organized magnetic signatures. Detailed mapping of field strength and structure around 3I Atlas could distinguish between induced magnetospheres created by solar-wind interaction and intrinsic fields generated by internal processes. Natural comets occasionally produce magnetic signatures, but these are turbulent and variable. Stable, organized fields would be harder to explain naturally. Communication payload proposals generated the most controversy. Should any intercept mission carry equipment capable of transmitting signals toward 3I Atlas, attempting to initiate contact if the object appeared artificial? Proponents argued that failing to attempt communication would waste a unique opportunity. Opponents raised concerns about revealing Earth's location and technological capabilities to potentially hostile intelligence without careful consideration of consequences. The Breakthrough Starshot initiative, originally designed to develop laser-propelled spacecraft capable of reaching nearby star systems, offered to contribute optical communication technology. Their proposal involved high-powered laser systems that could transmit information at extremely high data rates over interplanetary distances. Such systems could potentially establish contact with 3I Atlas if it possessed receivers, while also providing enormous bandwidth for returning scientific data to Earth. Particle detection instruments would sample the charged particle environment around the object, potentially revealing plasma interactions or particle emissions that might indicate power generation or propulsion systems. These relatively simple instruments required minimal power and mass, making them attractive additions to any mission, regardless of primary objectives. The instrument selection ultimately depended on mission architecture and available resources. Comprehensive characterization required multiple instrument types working together, but payload constraints forced difficult choices about which capabilities were truly essential versus merely desirable. The prospect of humanity potentially encountering intelligence from beyond our solar system forced immediate confrontation with ethical questions that had previously existed only in academic philosophy and science fiction. If 3I Atlas and its companion objects represented technology rather than nature, should humanity attempt contact? The answer seemed obvious to some and deeply troubling to others for entirely different reasons. The contact advocates argued from opportunity and curiosity. If intelligent beings were exploring our solar system, attempting communication represented perhaps the most significant moment in human history. Failing to try, they contended, would represent tragic missed opportunity driven by fear and excessive caution. We broadcast our presence constantly through radio and television leakage. Earth's technological civilization is already visible to anyone looking carefully. Remaining silent now seemed pointless. Risk assessment painted a darker picture. Broadcasting toward potentially artificial objects would definitively reveal Earth's location and technological capabilities to unknown intelligence whose intentions and capabilities remained completely mysterious. Contact optimists often assumed benevolent or at least neutral intentions from any civilization capable of interstellar travel, but nothing guaranteed that technological sophistication correlated with friendly disposition. Human history offered countless examples of encounters between civilizations at different technological levels, ending badly for the less advanced society. The zoo hypothesis offered one framework for thinking about contact ethics. This concept, proposed by radio astronomer John Ball in 1973, suggested that advanced civilizations might deliberately avoid contact with younger species, observing but not interfering to allow natural development. If 3-Eye Atlas represented such observation, attempting contact might violate protocols we don't understand and trigger responses we can't predict. Perhaps the objects remain silent deliberately, waiting for humanity to reach some developmental threshold before revealing themselves. Consent emerged as a thorny issue that traditional space agency decision-making wasn't equipped to handle. Any contact attempt, successful or not, affected all humanity by potentially revealing our presence to external intelligence. Yet decisions about whether to transmit signals would likely be made by space agencies or governments without meaningful public consultation or consent. Small groups of technical experts and political leaders would make choices with consequences for the entire species. Was this acceptable? Did anyone have standing to object? The active SETI debate provided relevant precedent. For decades, some researchers had proposed broadcasting powerful radio messages toward nearby star systems, rather than passively listening for signals. These proposals generated fierce controversy, with critics arguing that announcing our presence to the galaxy without international consensus represented dangerous unilateral action. Several scientists, including Stephen Hawking before his death, explicitly warned against active transmission, suggesting silence might be the safest strategy for young civilizations in a potentially dangerous universe. The 3-Eye Atlas situation differed in one crucial respect. These objects were already here. If they possessed intelligence, they had already found us through their own initiative. The question wasn't whether to reveal Earth's existence, but whether to acknowledge awareness of their presence and attempt reciprocal communication. That distinction didn't resolve the ethical dilemma, but reframed it in ways that made some arguments less relevant while highlighting others. Several ethicists proposed that any contact attempts should follow carefully designed protocols, including multi-stage approaches that gradually escalate communication complexity while monitoring for responses. Begin with simple mathematical sequences or physical constants that any technological civilization would recognize. Progress to more complex information only if initial signals generate acknowledgement. Not everyone accepted that 3-Eye Atlas represented anything beyond natural phenomena requiring better understanding. A substantial faction of comet researchers, planetary scientists, and orbital dynamicists maintained that gaps in current knowledge didn't justify invoking artificial explanations, particularly when comet physics remained incompletely understood and new observations continually revealed unexpected natural processes. Their position started with historical precedent. Astronomy repeatedly encountered phenomena that seemed impossible under existing theory, only to find natural explanations as understanding advanced. Pulsars, discovered in 1967, initially seemed so regular that researchers briefly considered artificial signals before realizing they were rapidly rotating neutron stars. Fast radio bursts appeared impossibly energetic when first detected, spawning exotic explanations, before observations revealed them as natural astrophysical phenomena. The lesson was clear. Mysterious doesn't mean artificial. Detailed modeling efforts attempted to explain the trajectory change through extreme outgassing scenarios. Perhaps 3I Atlas contained unusual volatile reservoirs, pockets of highly pressurized carbon dioxide or carbon monoxide trapped beneath an insulating crust. During perihelion passage, solar heating could penetrate deep enough to trigger catastrophic pressure release, producing brief but intense thrust without corresponding brightness increases if the geometry directed gases away from Earth's viewing angle. The models required special conditions, but special conditions weren't impossible. Subsurface cavities offered another natural mechanism. If the nucleus contained voids created during formation or carved by previous outgassing episodes, pressure could build in these chambers until structural failure released material explosively. The timing delay between perihelion and trajectory change might represent thermal diffusion time, heat gradually penetrating inward until reaching a critical threshold. This mechanism had been proposed for explaining outbursts in solar system comets and might apply to 3I Atlas with appropriate scaling. Rotational dynamics received renewed theoretical attention. Perhaps the nucleus had complex rotation, tumbling rather than spinning smoothly, with active regions distributed in ways that created net acceleration in unexpected directions. Computer simulations explored millions of combinations of nucleus shape, rotation parameters, and active region locations, searching for configurations that reproduced observed acceleration without invoking artificial propulsion. Some simulations came tantalizingly close to matching observations, though requiring assumptions about properties that couldn't be independently verified. The convergence on Saturn L4 represented the hardest challenge for natural explanations. Two objects arriving at the same Lagrange point seemed impossible to attribute to chance, but statistical arguments had weaknesses. Lagrange points occupy relatively large volumes of space, perhaps 20 million kilometers across. The claimed precision of the convergence depended on trajectory projections years into the future, which accumulated uncertainties rapidly. Perhaps the apparent precision was illusion created by preliminary orbital solutions that would diverge significantly as more data accumulated. The natural holdouts emphasized that extraordinary claims required meeting higher standards of proof than ordinary scientific hypotheses. Proposing new comet physics required only demonstrating that current models were incomplete, something already widely acknowledged. Proposing artificial objects required positive evidence of technology, not merely absence of complete natural explanations. Gaps in understanding weren't evidence of intelligence, just evidence of gaps. This philosophical position had merit, but struggled against accumulating observations. Each new piece of data, the Juno magnetometer readings, the organized radio emissions, the trajectory precision, added weight to the artificial hypothesis while requiring increasingly contrived natural explanations. The holdouts weren't wrong to demand rigorous proof, but their position was becoming harder to defend with each passing observation. If 3I Atlas truly represented artificial technology rather than natural phenomena, what level of engineering capability would that require? The assessment forced uncomfortable confrontations with the vast gulf between human spaceflight achievements and the capabilities implied by interstellar travel combined with in-system maneuvering. The energy requirements alone staggered conventional engineering. Accelerating 33 trillion kilograms by 200 meters per second required roughly 6.6 times 10 to the 15th joules of kinetic energy. For comparison, that equals approximately 1.6 megatons of TNT equivalent, or roughly 80 Hiroshima-scale nuclear weapons. Delivering that energy efficiently through propulsion systems operating in deep space implied technology far beyond anything humanity had developed. Propulsion system analysis explored what mechanisms could produce the observed acceleration without visible exhaust. Ion drives, used successfully on missions like Dawn and Deep Space One, provide extremely efficient propulsion by accelerating charged particles through electromagnetic fields. But ion drives produce tiny thrust levels, suitable for gradually modifying trajectories over months or years, but incapable of the relatively rapid maneuver 3I Atlas executed. Scaling ion propulsion to necessary thrust levels would require power generation far exceeding anything achieved in spacecraft engineering. Solar sails offered another possibility. Large reflective surfaces pushed by sunlight could theoretically produce acceleration without conventional propellant. But solar sail effectiveness depends on surface area to mass ratio and distance from the Sun. At 3I Atlas's post-perihelion distance, solar radiation pressure couldn't generate the observed acceleration unless the object was essentially a gossamer membrane rather than the solid nucleus observations indicated. The physics simply didn't work for massive objects. More exotic propulsion concepts entered consideration by elimination. Antimatter propulsion could provide enormous energy density, with matter-antimatter annihilation, converting mass directly to energy with perfect efficiency. But antimatter production and storage remain beyond current human capability, representing technology that might be centuries away if achievable at all. Any civilization deploying antimatter propulsion would be operating at technological levels that made comparison with human engineering essentially meaningless. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by energy utilization. Type 1 civilizations harness all energy available on their home planet. Type 2 civilizations capture the entire energy output of their parent star. Type 3 civilizations control energy on galactic scales. Humanity currently ranks around 0.7 on this scale, not yet achieving full planetary energy utilization. Interstellar travel, capable of the observed 3I Atlas characteristics, likely required Type 1 civilization status minimum, possibly approaching Type 2, depending on propulsion methods and mission parameters. The technology gap between humanity and any intelligence capable of building and operating such systems might be comparable to the gap between Stone Age humans and modern industrial civilization. We might be observing technology whose operating principles we couldn't understand even with detailed examination. If 3I Atlas represented artificial technology, where did it come from? Tracing interstellar trajectories backward through space and time offered one approach to identifying possible origin systems, though the analysis involved substantial uncertainties and assumptions that accumulated over the centuries-long journey such objects would require. Stellar kinematics provided the mathematical framework. Every star in the galaxy moves through space with measurable velocity relative to the Sun. By reconstructing 3I Atlas's trajectory before it entered the solar system, and comparing that path with the motions of nearby stars, astronomers could identify candidate systems the object might have departed from tens of thousands or even millions of years ago. The analysis identified 12 stellar systems within 50 light-years of Earth, whose trajectories brought them within close proximity to 3I Atlas's reconstructed path at some point in the past. The timeframes varied dramatically from 50,000 years ago for the nearest candidates to over 400,000 years for more distant possibilities. The uncertainties in these reconstructions were enormous, with error margins spanning light-years and millennia, but they provided starting points for targeted investigation. One system stood out for reasons beyond geometric alignment. Gliese 687, a red dwarf star located 14.8 light-years from Earth, matched 3I Atlas's trajectory within error margins for a departure approximately 470 years ago. That system had attracted previous attention from SETI researchers because radio telescope observations detected unusual narrow-band emissions at frequencies that seemed inconsistent with natural stellar processes. The signals were never confirmed as artificial, remaining classified as interesting anomalies requiring follow-up observation. The 470-year transit time implied average velocities around 3% of light speed, far beyond anything natural. Ejection processes could achieve, but potentially accessible to advanced propulsion technology. Interstellar travel at such velocities would require either extremely long-duration missions spanning centuries, possibly using generation ships or suspended animation, or propulsion systems capable of sustained acceleration and deceleration that remained firmly in the realm of theoretical physics for human engineering. Alternative origin scenarios included the possibility that 3I Atlas wasn't coming from any specific stellar system, but rather represented technology operating within the interstellar medium itself, perhaps part of a larger network or infrastructure whose scale exceeded anything concentrated around individual stars. This speculation ventured far beyond what observations could constrain but couldn't be ruled out, given how little humanity understood about what might exist in the vast spaces between star systems. The coincidence of multiple objects converging on Saturn L4 suggested they might share common origin, launched from the same source system in a coordinated exploration or survey mission. But trajectory reconstructions for the other candidate interstellar objects pointed toward different origin regions, implying either multiple source civilizations or a single civilization with presence across multiple stellar systems. Both possibilities raised profound questions about the prevalence and distribution of technological intelligence throughout the galaxy. The origin question remained fundamentally unanswerable with current data, a reminder that detecting potentially artificial objects provided only the first step in understanding their nature, purpose, and source. The realization came gradually, but carried profound implications. If 3I Atlas could change course deliberately, it possessed capabilities that fundamentally altered the nature of the encounter. This wasn't humanity observing a passive object drifting through space. This was potentially mutual observation, with Earth's technological civilization being studied as carefully as we attempted to study the visitor. The mirror problem started with a simple physical principle. Any civilization capable of detecting our telescopes pointed at them would know they were being watched. Modern astronomical instruments operate by collecting electromagnetic radiation, primarily visible light and infrared. This collection process is passive and undetectable at interstellar distances. But 3i Atlas wasn't at interstellar distances. It was inside our solar system, where even relatively modest sensors could potentially detect Earth-based observation campaigns. Consider what 3i Atlas would see looking back toward Earth. A planet orbiting in the habitable zone of a stable star, showing obvious signs of technological civilization in its electromagnetic spectrum. Radio and television broadcasts leak into space continuously, creating a bubble of artificial signals now extending roughly 100 light-years from Earth. Closer examination would reveal city lights on the night side, industrial heat signatures, atmospheric composition altered by technology, and satellites in various orbits creating artificial brightness in near-Earth space. The vulnerability extended beyond mere detection. If 3i Atlas possessed sensor systems sophisticated enough for interstellar navigation and precise trajectory control, it almost certainly could resolve Earth's surface features and potentially observe specific facilities. Major optical telescopes, radio antenna arrays, military installations, and population centers would be distinguishable from orbit with imaging technology comparable to what humanity uses for Earth observation satellites. We assume privacy provided by distance, but distance means less to technology we don't understand. Historical precedent from human exploration offered sobering lessons. When technologically advanced civilizations encountered less developed societies throughout history, knowledge asymmetry typically favored the more advanced group. The civilization with better reconnaissance, better understanding of the other's capabilities and intentions, held strategic advantages, regardless of whether conflict or cooperation ultimately resulted. 3i Atlas potentially knew far more about Earth than Earth knew about it, creating fundamental imbalance in any interaction. The observation campaigns tracking 3i Atlas involved dozens of major telescopes and hundreds of smaller facilities, all pointing toward the object at various times, recording its spectrum, measuring its position, analyzing its composition. If the object possessed even basic sensor systems, it would detect this attention as clearly as humans notice someone staring. The question wasn't whether 3i Atlas knew it was being watched. The question was what conclusions it drew from that observation, and whether humanity's response appeared threatening, welcoming, or merely curious. Communication attempts, whether through radio broadcasts, laser transmissions, or any other method, would definitively signal awareness and intent to interact. But silence didn't guarantee invisibility. Simply existing as a technological civilization on an easily observable planet in the path of potentially intelligent visitors meant humanity had already revealed itself completely. The timeline stretching ahead of humanity held specific milestones that would test every hypothesis about 3i Atlas and its companion objects. These weren't abstract predictions decades away, but concrete observation opportunities occurring within the next few years, events that would either confirm the extraordinary or reveal mundane explanations for currently mysterious phenomena. The immediate future focused on trajectory refinement. Every additional month of observations would improve orbital solutions, reducing uncertainties about exactly where 3I Atlas was heading and when it would arrive. By mid-2026, trajectory predictions would firm up enough to confirm or refute the Saturn L4 convergence with high confidence. If the object deviated from that destination, it would suggest either navigation errors, changed plans, or complete misinterpretation of intent. If it maintained course precisely, the case for deliberate navigation would strengthen dramatically. The potential intercept missions represented the next major decision point. NASA had until late December 2025 to commit to Juno redirection or lose the optimal launch window. SpaceX's proposed mission faced its own timeline, with an April 2026 launch date requiring funding commitments and hardware development starting immediately. Either mission succeeding would provide close-up observations by late 2027, 2 years before the Saturn L4 convergence, potentially answering questions about composition, structure, and nature that Earth-based telescopes couldn't resolve. 2027 itself brought significant developments. The first of the candidate companion objects would approach Saturn's orbital region, providing preview of what might occur when the others arrived. If 2025 QX 113 reached Saturn L4 and simply continued past on its hyperbolic trajectory, it would suggest the convergence was coincidental rather than intentional. If it decelerated, entered orbit, or exhibited any behavior suggesting controlled arrival, the implications would be unmistakable. The Vera Rubin Observatory's legacy survey of space and time would reach full operational capability by mid-2026, scanning the entire southern sky every few nights. This unprecedented survey would detect dozens, or potentially hundreds, of additional interstellar objects over the following years. If the candidate object count continued growing and showing similar convergence patterns, it would confirm a fleet rather than isolated visitors. If discovery rates returned to pre-2024 levels and new detections showed random trajectories, it would suggest the recent clustering was temporary anomaly. 2029 represented the ultimate test. 3I Atlas would reach Saturn L4 in late summer if current trajectory held. Whatever happened at that destination, rendezvous with other objects, continued transit through the solar system, or something completely unexpected, would occur in full view of Earth's increasingly sophisticated observation networks. The wait until then would involve 3.5 years of mounting tension, continued debate, and preparation for outcomes, ranging from mundane to transformative. Communication monitoring would continue throughout this period. SETI facilities worldwide maintained watch for any signals from the objects, any coordination transmissions between them, or any attempts to contact Earth. Radio silence had prevailed so far, but could break at any moment if whoever or whatever controlled these objects decided communication served their purposes.